My name is Gunnar Sletta. At least I've been to DevDays a couple of times before, but I haven't been here for 3 years or so now. So I see some familiar faces, but I don't know all of you, so I guess you don't know me either, so I can say a few words about myself. I've been with Qt and Nokia for about 8 years. I started out with Qt scripting for applications, for those of you who have used Qt long enough to remember that, a Java scripting engine. Spent a little bit of time with Qt script, but left that. I spent 3 years on the Java port of Qt Zombie, but most of my time and my passion has gone into the graphics stack in Qt. So most of, or at least significant parts of Qt Painter was my work for 4.0, and like the software paint engine that lives in Qt today, what we call the raster paint engine, was originally implemented by me. So that's my area. So about this scene graph project. When I mean we've seen a lot of, we've been able to do a lot of cool stuff with Qt over the years, and I've seen a lot of really nice interfaces. But it's a little bit hard to get there sometimes, and even with QML, there are a few things where I like to think that we could do a little bit better. And if we consider like what games are able to do, then like there's a little bit of a gap, right? And they can do these insanely complex scenes with millions of vertices on the screen and with blending and fancy effects and particles and all that stuff. And we like sometimes struggle to get a few like rotating buttons to animate gracefully. So like the main pitch for this project was to get user interfaces to run with game performance. That was like the main pitch. So the topic for the day. I'm going to talk a little bit about the graphics stack as it is today, how it works, and a little bit about what obstacles are in it, and how we can use QML on top of OpenGL to potentially remedy some of those obstacles. And I would invite you to interrupt me and raise your hand and ask questions along the way. If you do so, then please wait for the microphone. Robert will come out with the microphone and give it to you. We're recording all of this stuff, so if you're saying something, then don't be afraid to say something even though it's recorded. But since it's recorded, you need to have the microphone so that you hear what you're saying. So wait for the microphone, but don't be afraid to stop me along the way. If this turns into a discussion in this hall and not a monologue from me, then that's just fine. So let's move on to the graphics stack today. It's a very simplified view of how things work, but I sort of split it now into 4 layers. On the top, the application layers, the painter, the paint engines in yellow, and the underlying APIs in red. And like the way that this typically works, or the way that all of these work, they follow the same kind of pattern. If you consider the widgets, they start at the top level window surface, and then there's a paint event. You go into the top level widget, and you call paint event for that one. Then you open a painter on the widget. You go into some styling code and you draw that widget, and then you go to the next, like the next widget in the hierarchy could be a toolbar, and render the background of the toolbar, go into the styling code to draw the border of the toolbar, and then you go into the buttons inside the toolbar. This very hierarchical top-down way of rendering, widget per widget. WebKit has a similar model. It has this huge document and traverses this document by calling a paint function on elements in the DOM tree, rendering everything like paragraph by paragraph, text item by text item, image by image. And QML on top of graphics view follows the same pattern. It's a graphics scene populated with tons and tons of items. And if you have a button with a text inside, typical QML item, you have and you have 2 of those next to each other. You first go into one button, draw the rectangle, then draw the text, then you go into the other one and draw the text. And all of this stuff goes through this API called QPainter. And then underneath QPainter sits these things called the paint engines. And like, if you say draw a line on a QPainter, the software paint engine will do like turn into this midpoint algorithm and plot some pixels on the screen. The paint engine, or the GL paint engine, will go into this triangulating stroker, produce a triangle strip, and say GL draw erase. And the VG paint engine will convert the points into a VG path and call VG stroke path, which is then part of the underlying red APIs. So that's, I guess this is familiar for many of you, right? Yes? It's the paint engine used on Symbian. I forgot about the microphone. The question was, what is the OpenVG paint engine? And the answer is, it's the paint engine and the graphics system we are currently using on Symbian phones, like the N8. So not currently, on future phones. But it's released in Finland, right? Is it? Yeah. No. Yeah, and I took up those three engines because it's the three engines that we care mostly about. Whereas the paint engine, because it's the top-notch reference implementation, which runs fairly fast on all fairly modern hardware. GL, because it's the graphics API that the industry seems to standardize on, and OpenVG because Symbian is somewhat important for us. Perhaps not only somewhat, actually extremely important. Anyway, moving on. Can I get a show of hands? How many of you tried QML already? Or how many have tried it? How many are actually using it for applications? Not that many. Okay. Yes. The UIs are rendered hierarchically. And it's like all our APIs support and almost dictate this way of drawing. And it's item per item or widget per widget, and all the items draw their own content. And if you look at this particular thing on the side there, which is the Flickr mobile demo from the QML, the declarative demos in Qt, it's the same thing, right? There's a delegate responsible for painting each of these items in the list, and yeah, you can't really see that. Problem with bad. Oops. If I zoom in. Okay, so there's an alternating background color. It's like black and blacker. So like for each of these items, there's an alternating background color. There's a white rectangle behind, like around the image, like a white frame. There's the image. There's a text. Then there's a drop shadow on the title text that you cannot see because it's too dark. Then there's the content text, and the content text also has a drop shadow that you cannot see. And I mean, we have hardware acceleration today. You can if you want to use hardware acceleration with normal widgets, you just subclass QGL widget. Is there a hand? No. And if you use a QGL widget, you get the GL paint engine when you open a painter on that widget, and you have hardware acceleration. If you want to combine that with graphics view, you just tell graphics view that your viewport is a GL widget, in which case when you open a painter on the viewport of the graphics view, you get a GL widget and you get the GL paint engine and you have hardware acceleration. If you use QML, you can pass minus OpenGL, which in turn does the line above, which in turn does the line above again. So minus OpenGL installs a QGL widget on the viewport of the graphics view of the QMLC. And that way you have hardware acceleration, right? And you should be there. But no. And as I said, you can do awesome stuff with this already. But I think there is potential for improvement. So what is, like, we have all the things in place already. What are the things that are actually holding us back? And it starts with this thing called the painter's algorithm. And the idea is that the name comes from the way that a painter, like an artist painter with paint and canvas, paints his image. He starts out with, if you want to draw a mountain with a tree in front and a bird in front of the tree, the artist has to like paint the mountain, wait for the paint to dry, then he paints the tree, then he waits for the paint to dry, and then he paints the bird. If he's really good, he probably can like scissor out stuff, but usually you paint in layers on top of each other, and that's also what Qt does. So I mean, we start at the back and we fill everything in a back to front, item by item manner, right? So like we start. You can also not see the checkers here. I need to increase the. Can you see that there's some subtle gray lines? Yeah. Anyway, I mean, we start at the very back. We fill the screen with black, and then there's this texture overlay. Then comes a this alternating background. It's the white frame, and it's this butterfly on top. It's the text, and the text again. And if we look at just this one area here, we have background, texture, the alternating background, white, and then image. That's 5 layers, and we're actually showing only the frontmost pixel. And even though this is a pretty decent piece of hardware, it's still wasting a lot of resources. What if I could like do it the other way around and not draw the stuff that is hidden? So one way to get there is to use the OpenGL Z buffer. If I could draw the opaque content and sort that in a front to back manner, then I could draw the image first, then I could draw the white, and then I could discard the alpha background, this checkers or the diagonal lines that you couldn't see because it was too dark, and I could also discard the very black at the very back. Transparent stuff still needs to be naturally blended in the same traditional painter's algorithm way, because you want the transparency to behave properly. But at least for the areas of the screen where there is a massive amount of overdraw, you could just discard it. And in this case, that's like 20%, so yeah, that's significant. And another problem is that for each of these items, I'm like the GL hardware is typically set up to, you build a state pipeline or like a pipeline of stuff to do, and then you give it like tons of data, and then you set up another pipeline and you give it tons of other data. While what we're doing is that we're first saying we're going to do a solid fill with blending. That means we need to get a shader program for doing solid fills. We need to set the uniform on the shader program to set the solid color. We need to enable blending. We need to enable the vertex attributes for just a quad, and we need to send the data. And then like after doing all of that stuff, we send like 4 points. And then after that comes the white square. We're already set up to do the solid fill, and we're already set up to do the shader program is set, but we need to change the color, and then we upload another 4 quads, or like 4 points. Then we switch to the textured image, or to the image, which is we need to change to the texture program. We need to bind the texture. We need to set up the pipeline to do both vertices and texture coordinates. And we need to enable blending again, because that was disabled from the last round. And then there's like massive amount of state changes for every 4 points we send. And it's the same thing with the text. Text is also, even though it's still textured, it's using a different texture, and a different program on the GPU to actually do the texturing. So if we could somehow take all of this and reorganize that and sort of schedule it out of order rather than in the item-based order, then we could reduce all of these state changes down to just one for textures, one for solid fills, and one for text. So we're down to 3 compared to 3 times the number of items you have on screen. So just to illustrate how that would work, I would start at the front, draw the images, drew all the solid fills, all the texture thing, the background, and then the text. And the cool thing is that with QML, all of the items and all the content in this in the scene is more or less declared. So I can actually look at that entire scene and see which pieces can I merge together and which pieces can I draw in one chunk. Now naturally, I mean, QML has very strict ordering and stuff, so we can't reorganize everything, but we can at least do significant like cross full scene optimizations, things that are simply not possible with the QPainter model we have today. Questions so far? No? That brings me to the Qt Scene Graph project. And this is the one image that Sebastian stole from me that I didn't know about. Yeah. So like, if we take a look at the stack that I had before, we simplify this a little bit. We say we have QML, and then we have Graphics View Painter and the OpenGL Paint Engine, which is like the backend API for QML, and then there's OpenGL ES at the bottom. And if we take for a given that OpenGL ES is 2.0 is there at the bottom, it can be GL 2.0 desktop as well, of course. You just say ES because it could be in parentheses actually. But if we take that and we take out the middle part and replace it with this tiny little library called Scene Graph that just implements all of the QML stuff, then hopefully we can get a little bit more out of it. So like the bottom line here is really like it's all about improving QML using OpenGL ES 2.0 or OpenGL 2.0 desktop or later versions of OpenGL desktop. They all work. And this naturally brings the question, since we're talking about OpenGL, people tend to think about 3D, and it's really out of our scope. We're doing this to do really fast QML stuff. And this is also the reason why projects like Ogre and Open Scene Graph are not strictly relevant, because it's a huge lump of code targeted at big games. This is a small scene graph to help us get QML to run faster. Like the integration code with Open Scene Graph would probably be bigger than the entire Scene Graph library. So that's kind of out of scope. And anyway, if you're curious about QML and 3D, Sarah will be holding a presentation in this room just after me. So I suggest you stick around for that one. Anyway, going into a little bit of details on the structure. The scene graph is 100% predefined nodes. There's nothing to subclass. There's nothing. You can just use the predefined nodes we have. And the nodes we have is the geometry node, which consists of a mesh and an effect. And the mesh is basically just like, it's the triangle strip that represents some sort of geometry, like a tentacle or a rectangle. The effect is what to do with that piece of triangle data, like fill it with a solid color, or apply a blur effect, or do a particle thing or something. It can really be anything. It's a shader program, so and with a virtual activate function, so you can really like set up stencil and set up all sorts of cool stuff. How many of you actually saw the May post that we did? Back in May, we published the initial repository for Scene Graph, and we had some cool videos to show what we can do with this stuff. Very few people saw that. There are some cool videos. The other node is the transformation node. It's a 4x4 matrix, which means that it can strictly be 3D. But currently, we're only using it for 2.5D, so like perspective transformations and stuff. But it doesn't hurt to have a full-blown 3D matrix there in case you want to do some nice perspective transformations and things like that later on. And sorry. Then finally, there's the clipping node, and the clipping node is one of the things we were hoping initially to keep out of the scene graph tree, because we wanted to keep it really, really pure, and clipping could be done via an effect. But the thing is that the stencil is so insanely fast compared to doing alpha masking, so we just had to have it. So, in addition to the tree, I can actually explain the picture. If you go back to just see how like the scene graph would be composed for the list we saw earlier, we have like there would be a root, the root of the list. There would be a clip that prevents anything. Like when the list is scrolling outside of its bounds, it would have to be clipped. There would be a transform describing the vertical offset of the list. And then for each item, there would be geometry nodes that would sort of compose the various elements, the various QML elements of that item, like the background fill, the white frame, the image, the title text, and the content text. And this scene graph is then given to the renderer, or to a renderer, which looks at the tree and does something with it, sorts some nodes and reorganizes things based on whatever it thinks is a good idea, and then it renders that stuff. The default renderer that we have in the scene graph today will sort by either the set stacking or by material. And the reason it can be by Z or by material is that some hardware, typically embedded hardware, tend to have automatic set stacking. So even if you schedule arbitrary ordered, like arbitrary, if you tell an NVIDIA chip, what are they called? GeForce 800, for instance. If you tell it to draw something transparent and then a black square on top, then it will actually draw the transparent box and the black square on top. If you tell the graphics chip on the N900 to do a transparent thing and then a black box, it will actually wait with both of them until you say swap buffers, and then it will look at and say that like, oh, there's a triangle that is opaque in front of this transparent thing, so I'll simply not do that. So for the N900, the sorting actually doesn't give you anything because the chip already does that. So which is why like there on the N900, sorting by material makes a big difference. Which again brings me to the adaptation layer. So like I just mentioned that the N900 has behaves differently from a desktop chip, and it's not. I mean, that's not the only thing. For instance, when we do gradients, like the natural way to think of gradients is that you would just use color interpolation in GL. You would say that there's like black there and white there, and let GL interpolate the colors in between. And that's done using a using a varying in the GL shader program. But on the N900, again, if you do that, then suddenly you're wasting like 5 milliseconds per frame on a full screen gradient. And the reason for that, we suspect, is that this using a varying color will hit a worst case in the driver and do something nasty and slow you down. So on the N900, the best way to do a gradient is to do just use a texture, and that's 5 milliseconds faster per frame. So like the idea that we can actually adapt the rendering and the shader programs and all the stuff for a specific piece of hardware should make it possible for us to optimize significantly better. Another thing that we sort of built into the architecture is the ability to nest subgraphs of QML and use them as a texture source for another part of QML, and then potentially apply an effect to it, like colorize or blurring. How many have tried the Graphics Effects API? So, like, one of the problems we had with Graphics Effects API was that it's very easy to hit a non-performant path with that. Did someone experience that? Everyone that used it raised their hand again. Yeah. So we felt we needed to solve that, because that's like a key feature in order to do like really kick-ass effects and transitions and UI concepts, is to be able to actually like customize that stuff. And at that point, I guess you would like to see something. Wow, that was really fast. And Firefox is bouncing. I'll just kill it. Go away. So I'll do this main thing first. So I have my main QML, and over half of you had actually done some QML, right? If I remember correctly. So at least many of you will recognize this syntax, and Lars showed it as well on the screen today. So the idea is that I have my main consists mostly of this item, which has the ID effect root. It fills the entire screen with a little bit of margin. And then I have an image box, and I have 4 of these image boxes, and each of the image boxes, they take a different source, and I position them explicitly because the grid in QML scene graph-based thing doesn't quite work, so I had to position them positionally. But anyway, the image box is simply like a white square with an image inside. And if the root has the animation property set to true, then it will wiggle a little bit. So, and if I press the animate button, that's exactly what happens. It starts to wiggle. Right? Now the nice thing here is that I added this little colorize, which is an effect. It's based on this nested concept. It sources the effect root, which will effectively take this item out of the QML, the initial QML scene, hijack it, and stuff that into another render, which will render into an FBO, and then give me back the texture for that stuff. And I've given it, sorry. So there's like the root color, which is declared up here. The color is some pinkish thing. And I have this sequential animation on intensity. And I'll get into the actual content. I'm just going to show you how it works. So if I press the colorized, what happens is that it starts to do some weird stuff. And the way that this is implemented, if I click on this one, is that it's using this thing called the shader effect item. And we added this to the API like 2 weeks ago, and we're really uncertain if we dared to give like the raw power of GL shader programs to end users. But then we played around with it, and it was so really cool that I think we just have to have it. And so you specify a property, a string property called the fragment shader. You have to have cute_text chord, and we're debating with the, where did Sarah go? Okay. We're debating with the Qt 3D team because they also have a similar concept on their side for writing shader programs in QML 3D, and we want to standardize on at least the same names. So the name here might change, but the idea is that you have to declare a Qt text chord, the texture coordinate. You need to have a sampler 2D for the texture, and anything else that you do is up to you. It's the same thing in the vertex shader. You have to have a Qt_vertex position, a Qt_vertex text chord, and if you want to conform to the QML matrix, you need to use the Qt matrix. And presumably you want to write out the texture coordinate to the fragment shader. How many of you know GLSL? Not that many. Well, it's really like it's a very C-like language that lets you. The vertex shader is a program that you tell the GPU what to do with points. So you give it a point, and in this case, all that happens is that I multiply the point with a matrix. So like I send some points, and for each point, I multiply that with a matrix, which moves it to someplace on screen. And for the fragment shader, that's the program that is run per pixel inside each triangle. So in this case, I'm reading a texture. So I'm reading the particular part of the source image that I wanted to draw. I do this non-very proper to-grayifying, which will oversample. And then I mix the source and the grayed version with a colorized version of the gray thing. So fairly straightforward if you know GLSL. Probably a little bit obscure if you don't know GLSL. Well, this is run completely on the graphics card. There is a very hard standard set by me, at least, that we shall never ever do anything on the CPU, graphics-wise. I mean, we do the animation stuff and updating the QML stuff needs to happen on the CPU, of course, because that's all C++. But I mean, we should never do graphic stuff on the CPU. At least, I hope we can get away from that. But the really cool thing, which is also credit to the Qt 3D guys, is this concept of automatic property binding. In shader programs, you have like these thing called uniforms, which are that's like an input, a parameter that you can give to the program. So if you want to switch from solid color red to solid color blue, you would have a color specified as a uniform, and after setting that this is my program, you update the uniform to use like red or blue or white or green. And in this case, I declare the uniform low pvec4, which is basically it's a 4-component color, like red, green, blue, and alpha. And since I already have this and I have this property color down here, the shader effect item will automatically behind the scene bind those two together and bind the value of the property color to the uniform inside the GLSL. And I did the same thing with the intensity. So I have a float intensity here, and I have a real intensity here. And that's the thing that I'm animating over here. I set a sequential animation on the sequential animation on the intensity, and that's what's causing the stuff to wiggle in and out in terms of colors. But of course, I don't have to nest just one. I can nest as many times as I like. So I had this animated blur, which is based on the animated blur is based on a directional 8-point blur, which is a 2-pass 8x8 sample algorithm. So like the code for that is this one. Don't have to go into the details. You can look at the code when it's published later on. But anyway, if the colorize is active, I will source from the colorize. Otherwise, I will source from the effect root. So if I go back to my application, I can click on the blur, and it will start to blur while pulsing. Can you see? And of course, I can do this. I can nest as many things as I like. So I can also put on a drop shadow here, which is based on another shader that is put on top of that again, which is a 3x3 box blur put on top of the two-phase blur put on top of the colorize. And if I found QML scene, it's now running at 15% CPU. So now, this is a 4.5-year-old Mac. So it's not that much, really. And just to prove that I'm not joking, I mean, these are reusable components, and everything is written in QML, so I might as well just do the full thing. And have it all animated, nice full, like that. So that's now 1, 2, 3, 4, 5, 6, 7, like 16. Yeah, 16 indirect renders. And the scene graph will, because it knows about this concept of nested graphs, it will sort the graphs topologically and actually render all the FBOs in proper order. Where you, with the graphics view approach, you would typically go into a subtree, then switch to pixmap drawing, render the pixmap, use the pixmap as a source, switch back to the old one, and for some chips that would actually require like reading the Z buffer into system memory and copying it back again and stuff like that. So none of that. It's all like a clean render, clean render, clean render, clean render, render the full scene. Yeah, there's plenty of time, so I can do something else. I mean, I showed, you've seen the fragment shader. I can also do stuff with the vertex shader, of course. Say that I have this mesh resolution to be 10 by 10. I introduce a property real ratio. Questions, by the way, before I proceed? Yeah? Oh, wait for microphone.
Thank you. Two things maybe. One, I have to ask for my employer. Is there any possibility to get this for normal widget rendering? Because it would help quite a lot.
The problem with normal widget rendering is the way that it dictates this hierarchical item by item, widget by widget approach. We ran a project internally to take all of the rendering behind QPainter, stash that up into a similar data structure, and then reorganize that. But the cost of doing that per frame, because you don't have the full scene across multiple frames structure in place, so you have to build all that logic for every frame. Plus that the arbitrary QPainter commands, they're just deadly. There is so much stuff you can do with QPainter. QML is very limited in what it offers. So it's much easier to actually take the functionality set of QML and say that we optimize based on these parameters. So I don't see that you will get this for QWidgets, no.
Yeah, okay, thanks. And the other thing that interests me personally, you named computer games as the inspiring source at the beginning.
Yeah.
Computer games are pretty much the last real bastion of C++ coding. Did you ever think of using this for in-game GUIs? It probably would need a DirectX backend, but you have one, I think.
QPainter had a DirectX backend.
It had.
It had. It was removed in 4.6 because it wasn't supported and it was experimental and it wasn't really working. I mean, there wouldn't be anything. I wouldn't recommend using the scene graph that we have written for games. There are better scene graphs suited for games, but you could. I wouldn't see anything wrong with putting like this scene graph on top of a frame, like a game that is rendered, and use this to control the UI of a game. For the game GUI. And at least one scenario that we've been talking about is to have that you would first get a normal PaintGL call. You render your entire AutoCAD something 3D mesh and all that stuff, and then on top you follow up with a render the scene graph QML stuff, all in the same paint. So yes, I think that's a perfect scenario.
Okay, Gunnar, we have one more question here.
There was another one back there that was before, but okay.
My question is about the embedded world. So, as I understand now, as acceleration engine, you support only OpenGL. So, are there any plans for something else, or it's OpenGL only?
Right now, it's OpenGL only.
Mm-hmm. So, an embedded device should support OpenGL in order to take advantage of.
Yes.
Okay, thanks.
And I mean, if you ever played around with OpenGL and shaders, then there's no way back. It's just awesome. So you want to have that. There was the guy there.
How many FBOs are you using for the 16 images?
Sorry?
How many FBOs are you using for the 16 images?
It's one FBO per effect.
Okay, so
in that case, it's 16 FBOs. In this case, they are the same size, so we could strictly reuse someone and just bind in different textures. But given that many of the effect items will anyway be different size, there will be multiple.
Okay. Yeah, and regarding the what was just said about the interface, I'm actually working on a Qt-based game engine where we had the idea of using QML for interface. So the question is related to this: would it be possible to render the entire graphic scene into an FBO?
Oh yes, that's possible today. All widgets have a function called render that takes a QPainter. So if you just open a QPainter on a QGL frame buffer object, you can redirect an entire widget hierarchy into an FBO.
Okay, thank you.
I would like to show one more thing before we move on to the big line of questions. I mean, I showed the fragment stuff that you've seen by now, but I also wanted to show that you can do stuff with vertices as well. And so I created this property ratio, which is a float, and then form IP float. I was speaking to the creator guys yesterday, and they admitted that they would have to add support for GLSL inline in QML at some point after this. But we'll see what comes out of that. So what I'm doing is that I said that instead of just being a textured quad, I actually turned it into a textured mesh that is with 10 times 10 quads. and then I just want to do something with the X and the Y. It's not going to be sensible at all, but it is like to illustrate that you can actually do stuff with the entire mesh. So if I just do something like this, ratio plus cute text chord X plus cute text chord Y, I think that should give fairly funky results. Maybe multiply them together, even worse. And then I do a number animation on this. Loops is animation infinite from 0 to 1, running true, duration like 2.5 seconds maybe. Let's see if this works. Yeah. And of course I can animate it, and so I can do this on a live subtree and it doesn't really cost me anything. So that's it's certainly, that's one of the things that I like with the scene graph stuff. It opens up quite a few new possibilities in terms of what we can potentially do. Yes, my presentation was written in QML, by the way. That was my first. This was actually my first QML application. That's it. Then there were more questions. A few, yes. I don't know. I think maybe okay. Yeah, just pick one.
So I'm going to be cheeky and do two questions. The first one, back at the start, you talked about reducing overdraw to improve speed.
Yeah.
That would imply you think you're fill rate limited, which I'm really surprised by. Geometry setup I can believe, but I can't believe you're fill rate limited for 2D drawing. But do you have numbers, or is it just
not on this one?
Okay, fair enough.
On this one, or not exactly not this one.
Yeah,
but
okay.
Similar things to this.
So fill rate's still a function, even not just geometry setup. But
it's also like the fact that you have blending enabled. That's an extra step in the GL pipeline. So if you have a full screen drop, like a full screen fake drop shadow by just having an alpha rectangle and a full screen box on top, it actually can be noticeable even on a desktop. So it certainly is noticeable.
Okay. So second question, you were talking about the software rasterizer still being the reference rasterizer. Mm-hmm. So I'm actually going to be integrating Qt as a widget scene into an open scene graph project. And the problem is that we can't actually use the OpenGL backend because the way OpenStreetGraph manages threads and the way QGL doesn't manage threads, essentially we are looking like we're going to have to do all the Qt drawing in a Q image separately. So is it the case that when you say you want to do everything on the GPU, that at some stage there won't be a software rasterizer, or is it that you think that the GL is going to enhance its threading ability sufficient that we can run the QGL shaders independent of the existing scene shaders and not have them all go horribly wrong, which is what currently happens?
The answer is 4.8. Yes, I'll talk about that in my talk tomorrow on performance, but we'll get proper support. We added some threading support for GL to 4.7, and it's actually possible to do the full painting stuff with multiple painters on different FBOs and different threads. Maybe I have a demo of that lying here actually. Is it this one? Yeah. There's a bug in this demo, so it will crash in a second. Just so that it's clear. But this is 4 individual 4 times 2 GL widgets, each running their own thread, and yeah, painting seems to work. Good. Great. Nothing better than that.
Okay, next question.
Hello. Yes, since you are dropping QGraphics and QPainter from the, I mean, they are being not used by the SceneGraph project. Can we get to the point where there is no dependency on the Qt GUI module?
No dependency on the Qt GUI module?
Yes, because you are using only QML and the OpenGL ES backend.
What about, like, we still need to have the support for Windows, like getting Windows on screen.
Yeah, but you don't need 100,000 widgets and stuff like that, which is 15 megabytes of data you need to compile and put on your embedded device without using them.
So that's really the question. Are we going to modularize Qt better? Yes. The answer is that it's something that we want to do, but it's taking us a while to get there. I think we'll see that like, especially the GUI module has grown and grown and grown and contains now a lot of different things, and you're never using all of them at the same time. So it would make sense to split that into different modules. So yes, it's something that we've been discussing internally for quite some time, but to get to that point is really hard because it implies all sorts of stuff and politics and potential binary compatibility breakage, which I know that nobody likes. So, I mean, it's not so simple, but I hope we get there someday. Yes, let's not talk about that.
Well, this seems very nice, and I've been reading about this for a while. But I've been wondering how to handle not so well-behaved primitives, like the ones we would do with Qt on Canvas in Qt Quick, or for instance the primitives we nowadays do using C++.
So I mean, eventually we'll have to have some sort of plugin API too that can support painting, and that can support using maybe the native SceneGraph stuff. And I mean, there's been talk of maybe using like a WebGL Canvas 2D element inside QML. I mean, there's tons of options there. So we'll see what we end up with in the end. But yes, we'll definitely have something.
Is there now some kind of C++ SceneGraph base class in this implementation? What is the SceneGraph item? How have you done that?
The way that we did it so far is that, I mean, when you write in your QML file, you write import Qt 4.7. What actually happens is that this will trigger an internal plugin inside Qt Declarative to be loaded. And this internal plugin will call QML register item on various classes like the Q declarative rectangle, Q declarative image item, all of these, which end up being the rectangle. You can use the rectangle item and the image item and the text item, right? That's how declarative works today. The way that the SceneGraph works is that when you say Qt import Qt 4.7, we just instantiate some other items, and it's really just like hidden behind the scenes. There will, I mean, in terms of plugins, today there will be the Q declarative item that you would subclass. We would need to have something very similar to that, so that it's just a matter of replacing the base class. But other than that, there is, from the QML side, there is absolutely no change. Does that answer the question?
Not really. I think that the question was that how do you integrate this type of foreign objects, like when game surface or kind of an EGL buffer the Qt knows nothing about. So I think,
well, it needs to somehow get it to the SceneGraph, and if it's an EGL buffer, then that's something we would have to have some low-level plugin that could actually take the EGL surface and get that into something that we can source as a texture, and then we could represent that in QML as whatever that thing needs to be. It's a plugin API that just needs to be decided on.
But are you in charge, or who is in charge?
I will eventually figure out a solution for that. It's not in place yet. I mean, this is research stuff, and it's ongoing. So all I can say is that yes, we'll have something.
And then there is one more question: that how many contexts were here now on these demos? One.
Well, the threading demo had 8 or 9 actually, but the scene graph stuff has 1.
And if the hardware supports multiple contexts, then like this design will either run on one context or multiple. Have you decided that one?
I think we should stick to 1. One. Was there a follow-up question, or?
No. I think that we have to little bit think, for example, like the Google Chrome browser works and these EGL surfaces, and so that if you thread them same way as the tabs.
Yes. In this case, you would set up 1 scene graph per tab, and each scene graph would have its own context. You wouldn't want to use multiple contexts for the same scene graph.
Yeah, but if we talk about the embedded device and you for some other protection reason have structured the system same way as in Android, they have these different UUID, GUID pairs for different access on the system on the low level. I'm talking about the whole window manager for the whole device.
Yes, different topic.
But isn't then that also a scene graph?
Yep.
If you would follow this design pattern.
Yes. And that would be its own context. That would probably source EGL images from other scene graphs. At least that's how it would look today.
Any more questions?
You should talk to the Lighthouse guys, by the way. Yeah.
One more question. Do you support texture mix mapping and binary filtering?
Bilinear filtering?
Yeah.
We don't have explicit mipmap generation of the FBO sourcing right there, but that's just we can just add it.
Okay, cool.
It's and linear filtering we already have. You just set the item to be smooth.
Is there going to be a public C++ API to scene graph?
To be decided.
Would be nice.
Maybe. It would also maybe be disastrous, because then suddenly we cannot change it and we couldn't do that awesome optimization that would make QML 2 times faster. It's a really tough decision, right? Because the second we open up a public API, it's like, it's locked.
Yeah, but isn't that true anyway for the API you provide from QML?
The API we provide for QML is locked.
Yeah.
But we can still change all the backend stuff.
Yeah, but you could just provide the same API in C++ at the same level, I'm thinking. Or similar.
Maybe. We'll see. Yeah, you can always copy it. There's another question back there.
In your QML script of your example, you defined the source of an image from a file. Is it also possible to define it from a memory buffer?
That's a QML feature, and no, that's currently not possible. QML images are sourced from resources. But I think that's something that's on the request list for QML. But I mean, that would require that you had some way of creating that memory buffer in QML, and that kind of also contradicts the concept of declarative. So maybe not. File a suggestion to the QML guys on the bug tracker. There's a question over there.
the shader programs will only be available in the scene graph QML viewer, or could they be a separate feature earlier with the OpenGL backend?
For QML, like the shader effect item?
Yes.
It is theoretically possible to do that with the current stack by hacking on the graphics effects and stuff. But the problem is that, as I pointed out earlier, it seemed that everyone that had tried and gone down that road had run into performance problems. So it's not given that it will run as smooth as that. But it should be possible. But because the performance is potentially so disastrous, there's really not that much point. I think we're anyway running out of time. So if there's no more questions, then I thank you for your time.
Sorry, could you please stay a bit? I still have an announcement. One is the talk tomorrow in the morning. Wait a minute, I just need to sort my papers here. We had a change.